You can start now.
Okay, sir. Greetings to one and all present here for the IEEE International Webinar Series SAVANT. I am Dharini V, IEEE Student Chairperson of Women in Engineering Society from the Department of Electronics and Communication Engineering and behalf of the Institute of Technology.
Class
Here to
கவனிக்கணும்
walk for
ஸ்பெஷல்
today's
கிளாஸ்
session.
எழுதணும் அப்படி இப்படின்னு போயிடுச்சு.
Can you all please mute your mics? Yeah, thank you. Now I request Dr. C. Gnanakausalya ma'am, Professor and Head, Staff and Student Affairs to take over and address the session.
Thank you, Dharani. Good day, Professor Ming teach LIN, and good morning, dear participants. And this is Dr. C. Gnanakausalya, Professor, Department of ECE, St. Joseph Institute of Technology, St. Joseph's Group of Institution, India. I would like to extend warm welcome on behalf of St. Joseph Management and IEEE Women in Engineering Organizing Committee to Professor Ming C. Lin, Distinguished Professor, University of North Carolina, USA. Professor, your acceptance of our invitation to be a guest speaker in 7th webinar series is most graciously acknowledged. Professor, your presence here today is of great significance to us. Welcome you. In this platform, I would like to mention our sincere gratitude to our chairman, sir, Dr. B. Babu Manoharan, Managing Director, Madam, Mrs. Jessie Priya, Director, sir, Mr. Sashi Shekhar, and Principal Dr. P. Ravichandran for their continuous support to us. Dear participants, welcome you all to this 7th webinar series. I assure you again that you all find the series highly engaging, fruitful, and beneficial for your future venture. Welcome all. Thank you. Now the session is over to Dharani, IEEE Students Women in Engineering Society Student Chair, to introduce today's session guest. Dharani.
Thank you, ma'am. Now I have a few words to share about our eminent speaker. Dr. Ming C. Lin is currently the Elizabeth Stevenson Erie Chair of Computer Science at the University of Maryland College Park and John R. and Lewis S. Parker Distinguished Professor Emerita of Computer Science at the University of North Carolina, Chapel Hill. She is also an honorary chairperson at Tsinghua University in China. She obtained her BS, MS, and PhD in Electrical Engineering and Computer Science from the University of California, Berkeley. She received several honors and awards, including the NSF Young Faculty Career Award in 1995, Honda Research Initiation Award in 1997, UNC IBM Junior Faculty Development Award in 1999, UNC Hettelman Award for Scholarly Achievements in 2003, Beverly W. Long Distinguished Professorship Award in 2007 to 2010, Carolina Women's Center Faculty Scholar in 2008, UNC WOW Scholar from 2009 to 2011, IEEE VGTC, which is Virtual Reality Technical Achievement Award in 2010, and many Best Paper Awards at international conferences. She is also a fellow of ACM, IEEE, and Eurographics. So before we start the session, I would like to say a few instructions to be followed by the participants. Kindly post your queries and questions in the chat box. There would be a question and answer session in the end of the talk. The attendance link will be posted at the end of today's webinar. Now I invite our speaker of the day to kindly start the session. Ma'am.
Okay, thank you for the introduction. Hi, everyone. I wish I'm there in China. Unfortunately, we are in COVID-19 pandemic. Things are still under control here. Not quite under control here, so I can travel. So today I'm going to be talking a little bit about some of the work and research that we have done on learning-based traffic reconstruction to autonomous driving. And these are work that jointly done with my PhD students at both UNC Chapel Hill as well as University of Maryland at College Park. In the United States, the extra costs are estimated to be about $160 million for mobility. That means moving around from one place to another. This is roughly, just to kind of give you some idea, the Kuwait GDP in the same years around 2014. And the cost of a mobility has been increasing, pretty much consistently over the years. There was a little dip around 2008 due to Great Recession in the US. And probably there will be a little bit of dip right around this time due to COVID-19. But generally speaking, the cost of mobility has been going up over the years. Worldwide automobile production also has been increasing, as you could see on this chart, from 2000 to 2016 in millions of vehicles. And this is also indicating that the frequent use of vehicles, automobile vehicles around the cities, around the world, doesn't matter where you are. So today I'm going to talk a bit about some of these issues regarding how can we possibly use machine learning technique to help us visualize what's going on for traffic, and also reconstruct traffic flow and animation and visualization directly from these data that we have collected. Then I'm going to talk a bit about collision avoidance for multi-robot systems, including autonomous vehicle in very complex urban environment. Then I will talk a bit about how can we learn driving through visual analysis of simulated accident. So first, I'm going to talk about the city scale traffic animation using statistical learning and meta model-based optimizations. This is the work that I have done with my students and postdoc, Wei-Zi Li and David Walensky. The work was published in 2017 in ACM SIGGRAPH Asia. So as many of you know, urbanization is a fact, and it's a trend that will be here to stay. It has been estimated by 2030, there will be about 8.5 million people on Earth, and 90% of that population growth will be in emerging economies. Most of these people will be choosing to reside in the city. By about 2025, 5 billion people will be living in the city, and about half of those will be living in Asia, and a good number of them will be in India. So it is pretty much decided we need to solve the traffic problem. And so let's take a look at what's kind of going on. Where are the trends, and as we go from the years to years. So here in this chart, these two side-by-side chart, you can see the ridership by different mode, by subway, buses, bike, ferries, and ride-share services. In the early 2012 to 2013, the ride-share services practically doesn't exist. Now there are ride-share services like Uber, like Lyft. Yes, question? Was there a question? Okay, so there are ride-share services like Uber, Lyft, taxi, Didi in China, and the equivalent in India. That has been increasing. With the ride-share service, how is the traffic? Well, it turned out with the ride-share services, it actually makes traffic worse in New York City. Much, much worse, as you could see right here. This has changed from practically non-existence to it become a significant mode of transportation. So with ride-share services, even though now going from places to places is becoming more efficient, where the technology is actually helping us, but also including traffic jam. So the problem here is pretty clear. that traffic has become a major issue in the real world that we live in. So how do we address this problem? So this talk, I will talk a little bit about one possible approach, and that is to reconstruct city scale traffic, to be able to analyze what's going on, understand the cause, identify the bottleneck of traffic jams, and then we can design new policies to help police the traffic and help to redirect the traffic. And this also have a motivation in things like 3D virtual Earth, like Google Earth, where you can actually visualize what's going on in the city, but most of the Google Earth maps that you visualize has no traffic. So imagine that if you can see Google Earth with traffic, real-time traffic, that will show you how things are moving around, how helpful would that be for you to make decision regarding which route you're going to take, which highway you're going to adopt, and what possible direction you might go, and how you might travel, either by car, by subway, and various options that might be available to you. Another possible use for such a technology is virtual driving simulator. This is a great platform for a lot of drivers to learn how to drive, and it would help a little bit of decreasing the traffic as well, for not having to teach teenager how to drive on the car. I have a daughter, so I know exactly how this tool can help us improve driving and teaching teenager how to drive. But it also can be used as a simulator for autonomous vehicle. And so this is one of the use that we have also started adopting by taking traffic data, recreate the virtual traffic, and bring it into the virtual simulator for testing autonomous driving. So most of the virtual world needs some sort of contents that including draft traffic. And so this, as I mentioned, has several possible motivation. But the basic problem is that imagine that we have a virtual world, a digital world, whether you want to use it for visualization, whether you want to use it for entertainment, or whether you want to use for design of an autonomous vehicle. We need to create contents for this virtual world. And this content particularly, we are looking at is city traffic. And that is how to generate realistic real-time traffic flow using real world data to enable virtual world application. There has been some work that has been done in this area, and much of that work actually started from my research group, our research group at UNC, and it has been picked up by many of the different groups around the world. So one of the things that we have been looking at, and that's closest to what I will talk about, is traffic simulation. Traffic simulation is a way of simulating traffic on highway, on surface streets, on freeway, on city, in the city, out there on the urban environments, or out there in the country, depending on what you are interested. And there are many, many different techniques for traffic simulation. Some of the most recent work, including the one that's being shown here, these are the work that we actually used, we have actually developed in our group, is that we've been looking at how can we take traffic sensor data and then use that to help create animation of how the vehicle moves on the highway. And this is one step toward what I call the traffic reconstruction. Now, you might ask, what other kind of traffic data am I talking about? There are actually many in-road traffic sensor. For example, as you can see in this picture, you might have video camera that's mounted on top of a highway, like in this particular location. This is a close-up. It could be in-road sensor, like piezoelectric sensors, like a loop detector. It would record how fast a car has passed through a certain location on the highway and what's the density of the car. And also radar, lasers, and magnetic strips or dual lasers. All these are different kind of in-road traffic sensor that are having installed on the highway, on the road, to actually record the speed of traffic flow or how fast the car are driving. When I talk about city scale, I'm talking about city scale like city of San Francisco, city of Chennai, Bombay, New Delhi, New York City, Chicago. These are what we call the city scale problem. And previous reconstruction work mostly focused on a very small stretch of a highway that are just extremely small, as you could see here. This is a small stretch. We're looking at example like from some of our earlier work, just a very small segment of highway, or a small segment of freeway, or a small segment of roads. This is where the pre-prior R has been. Reconstruction of traffic with a very, very limited spend, it's a challenging problem already by itself. But imagine that you have to do it for the whole entire city. We're talking about a whole entire city of San Francisco compared to just a small segments of the highway. And you can see the scale of the problem. This is a small scale of what the prior work that has been done. We are looking at reconstructing traffic for the entire city of San Francisco. So this is very challenging. We are also looking at using devices that are not just limited to the in-road sensors, like most of the prior work has been. We are looking at devices like GPS devices, mobile devices, like your cell phone, that will tell us where you are and how fast you are going. And so this is the kind of data that we use in our work. Now, GPS has very broad coverage. And so this means that it can cover a very large regions of a city, even though that there could be a varying density. And there are many GPS data available through different carrier. For example, you could have GPS data available through Mobile Millennium. This is a traffic center at UC Berkeley. Or you could have Uber, which is a share ride company that release some of its Uber data that show you how the Uber traffics look like. And there are many more. I have listed a couple here. And so there are a lot of GPS data available that we can build on and we can use to test. So what are some of the challenges and what are some of the problems? Well, the issue is that most of these GPS data have very low sampling rate. That means that the timestamp differences can be large. Usually we're talking about more than a minute or more than 60 seconds. And one timestamp, just imagine how fast the car can travel in 1 minute. If it's on the highway, it's pretty substantial. And so just the one timestamp of more than a minute or two, you could have already traveled more than a couple streets. Here's a perfect example. At t equal to 1 second, the car may be right here. At t equal to 2 seconds, the car may already have traveled through multiple street segments to this location. And so the reconstruction problem basically asks, well, what's the travel time on each one of the road segment? Like how much time did the car spend here? How much time did the car spend here? Where is that 1 second being spent? Also, as you could see from this particular illustration here, there are actually two possible routes that the car can take from time equal to 1 second to time equal to 2 seconds. This is one possible way. What would be the other alternative? Well, the other alternative could have been here. The car could be going from here to here, for example. And so this is what it's called, commonly called the map matching problem. Now, if you know a GPS location is somewhere around here and somewhere around here, you know it's actually off the road. Both locations, it's actually telling you that GPS that's being carried by the driver is off the road. How can that be? The car is actually on the road. So there are actually some sensor imprecisions. This is not uncommon, particularly for GPS. And so one of the problems that we need to work on is to find the closest location to bring the GPS point back onto the road so that you can identify the appropriate road segments. And as I already alluded to earlier, Even though it could be right here, we need to map it back onto the road. If we map it to these points, and for the starting location and the ending location, we might pick this path that the car has traveled. Or we have started from this location, and that location, we could have picked this other path. So there are multiple possible solutions, as you can see, for this just, a simple, very, very simple problem of a map matching problem to be very difficult to solve. So there are different approach. One possibility is to assume that the car would take the shortest path or the shortest distance. And using this approach, multiple technique has been proposed. Or you can look at things like congestion network. Where are the traffic jams? Trying to avoid a traffic jam. Or you can look at empty road network and using only geometry information to infer it. Now, our approach, and there are also other approaches that look at travel time. How much does it take when you go from this location to that location? It could be 0.7 of a second being spent here and 0.3 seconds being spent here. And there are multiple different approaches. Some of them are more deterministic, some of them are probabilistic. And what we have done is we actually adopt a combination of these approaches. Now, there are some challenges that are really critical, and I'm going to talk a little bit about this machine learning approach that we are looking at. So there are some, as I already mentioned earlier, sampling rate is one problem. The other problem that we encounter is spatial sparsity. And basically it means that the GPS data that we get does not cover a city well enough. For example, right here. Here you see very, very little density coverage. So there is insufficient data, but traffic is dynamic. So using static methods of finding the shortest route or the one that takes the shortest time, it's insufficient. So the problem that we are looking at here is, given that you have a GPS data set, what you want to reconstruct is a city scale traffic that has low sampling rate of GPS data and also spatial sparsity. So our approach is to use iterative refinement that would reduce the errors that we started by using some sort of initial guess. We also don't use static interpolation. We use what we call a dynamic interpolations. So to kind of give you some idea, I will not go into all the detail, but I hope to give you some of the basic idea of what's going on here. So for data that we used, we are assuming that our input, including the GPS data, we have a digital map of the city that the GPS data are collected from, and we also have the trip record where the car has traveled in terms of the GPS location. This, however, the trip record is optional. Then what we do is we go through an iterative process, what we call a statistical learning process, where we started with some sort of initial guesses. We perform the map matching to figure out, given two GPS points, which route the car might have taken. We use that as our initial guess. We combine it with statistical learning to estimate the travel time. And this is an iterative process until we get it right. So we call this also a bi-level optimization, where we started with some initial guess. We guess the route you take, we try to match the travel time, and we go through this iteratively, refine different paths, refine the travel time until it converges. So it's converging between the travel time and the path it traveled. So this is an iterative refinement process. And this will give us a partial reconstruction of wherever that we need to go. As you could see, we would do this for different segments of the traffic at different locations using a large set of GPS data. Once we had that, we have a pretty good coverage of what we need. And this is what we call the initial optimization. It gives us a fairly good estimation of where the traffic coverage would look like. And this bi-level optimization is basically, we started with very coarse data, and then we try to refine it using both this map matching and the travel time estimation. But all this is assuming that we have static data. As I already mentioned, what we are really doing is we're actually doing dynamic data completion. That means we actually take into account of the movement of the traffic. So the dynamic data completion actually use a slightly different technique. We started with our initial estimation. Then we have these variable sampling depending on the locations. Now we also assume that these vehicles will be traveling following the traffic law and traffic equations. So as we start using the path that a vehicle would have traveled, we also have a collective traffic movement of the equation that we use to describe the collective traffic flow, not just individual traffic or individual vehicle. So a collection of traffic is what we assume that we have. And we will use that by using the traffic equations that would describe the overall traffic flow of the simulation to simulate the traffic flow. So we would use a combination of our initial guess and the traffic flow equation that describe a high level traffic flow that is a collection of a vehicle to simulate a traffic flow. And then we go through various decision points. What are the decision points? The decision points that we include, do you stop at the traffic light, like what you see here? So we need to also simulate the traffic light and the motion of the individual traffic vehicle around the traffic light. So these are large scale simulation that we are incorporating. So we have partial accurate reconstruction based on the GPS data coverage. And we have this iterative process and bi-level optimization to give us the information that we need. Once we have that, we combine it with traffic simulation that will give us a much, much broader coverage and also dynamic traffic flow across different intersections, across different highway using traffic equations. We also have a meta model, and the meta models are essentially a stochastic simulation that will simulate all these different probabilities, distributions at different road network, and also decision-making points at different traffic light, and a turning ratio, how many cars will turn right, how many cars will turn left. Some of these are very probabilistic. And so these sets of equations are the traffic flow equation that are collectively for large scale traffic flow, not individual vehicle. So what we are doing here is combination of individual vehicle that we have from GPS data and also a large scale traffic flow for collections of vehicles, how they move at different locations. So you can see we actually are simulating at a different level and reconstructing the traffic at a different level of granularity. And so we make these optimization and we make simulations and we use these meta model to help us do the fitting. And this is, again, this is a machine learning process. This is a full pipeline as we go through. It's using the optimization process to help us decide how it will converge to the final reconstruction of the overall traffic flow for the whole entire city. And it's very complicated because we actually have to simulate the whole entire city this way. So we perform both the local optimization as well as the global optimizations. So hopefully that kind of give you some idea. So the initial traffic reconstruction data, we use that to actually analyze the traffic flow. And as you can see here, our work actually improved against the prior work. So you can see our results here. We achieved the best simulation results in terms of accuracy. It has the lowest errors. The blue is ours. It actually have the lowest error, as you can see here. And it also it outperformed all the other in terms of accuracy. The error rate, the accuracy we have, it's about less than 20%, less than 10% of errors when compared to the other approach that are currently known. We have been able to reduce the error rate up to 97% relative improvement to the state of art, as you can see here in purple and green. And also the data completion parts, we actually have been able to also further improve the air by reducing it down to 7.8%. The overall speed up is also very impressive using the approach I just mentioned. This is faster than all prior work, and we are doing this for large city scale. The highest level of speed up that we were able to achieve is almost 2 order of magnitude performance improvement. So we also use to help us visualize what a traffic look like at different regions of San Francisco, as you can see here. For example, this is what the traffic will look like in terms of a coverage, the density map. The higher or the redder and warmer the map will look like, it means the higher the traffic. And so you can see on Sunday, the traffic flow, it's not so much, the traffic is lower at 9 a.m. On Tuesday, the city of San Francisco is very busy. And here are the hot spots. This is where the traffic jams are located. On Thursday noon, this is what the traffic will look like. And this is what it looked like on Friday, 7 p.m. And so we have been able to get all these visualization of the traffic at a different time using our technique. So overall, what we have presented is an effective algorithm reconstruct city scale traffic from sparse GPS data using statistical learning as well as a meta model based optimization to dynamically interpolate missing data where there was not enough data. And so we use traffic simulation to fill in the gap there. Our reconstruction enable modeling and visualization of city scale traffic, as well as data-driven traffic animation in a virtual environment. So next, I would like to just briefly mention, even though that our technique has been used to focus on simulation of traffic, many of the techniques that we look at can be generalized to reconstructions of movement for multi-agent system, like fish, like birds, like insect. It can also be generalized to other domains, such as learning from mobile sensor data. Doesn't have to be traffic data. It could also be data that are embedded in the environment. And we are also looking at what we have done here is using a combination of local fitting that will fit local data as well as large scale motion reconstruction. It means global data. So these are the kind of techniques that are generalizable to other domains. Next, I'm going to talk a little bit about unified collision avoidance for multi-robot system in arbitrary complex environment. Collision avoidance is a really complicated problem. Basically, it's the problem of how, if you have an agent or a robot or a car, how do you avoid running into another car? How do you avoid running into a pedestrian? And if you have a very complex environment, this is a really challenging problem. So I'm going to use videos here to actually kind of give you some idea how our work works. So the goal here is to develop a unified approach for collision avoidance. We make some assumption. We assume that these agents are disc-like shaped like the people, the pedestrians. They have no dynamic kinematic constraints. Their motions are mostly linear. There is no uncertainty. And we are also looking at how can we possibly extend it, these disc-shaped like agents to other more general like car-like vehicles. And these are both very, very challenging problems. They are difficult to solve. So what we have been looking at is we are looking at approach that are also scalable. We want to be able to handle hundreds and hundreds of cars and thousands of them if possible. And so we need to look at approach that are generally speaking that can extend it to a large number of agents or a large number of car and vehicles. So what we want to do here is to also be able to incorporate uncertainty. That means that we don't always know where the car is going to go next. And so the technique that we have developed here is essentially based on the idea of computing a probability fields for every single vehicle. we compute a probability field of the motion for every single vehicle based on its current positions and velocity. Where is the car most likely be driving towards? And once we are able to compute that, we will incorporate uncertainty into that probability field. And we will also take into account the dynamics of the car, the kinematics of the car, and the possibility of avoiding other agents that are in the environments. Then we will WAP it based on the environment and the trajectory that the car will drive. Okay, so the WAPing of that probability field is what we use to incorporate nonlinear motion. So what we computed is a probability field for straight linear motion. However, the roads are curvy. And to incorporate curved road, we WAP the probability field. So you can imagine the field we computed with the probability will now be able to WAP and curve around with the roads. We also WAP the shape of the car, as you will see here. We will also WAP the probability field for the car that you would drive based on the road shape and various agents. So if you're driving the straight, the probability field will give you the probability of collisions. And if you have other car, you have other obstacles like the blue cylinder that you saw there, those are obstacles. Then the car's probability field would try to avoid those. It would slow down or accelerate when there is no car. So you can see the car, when it comes close to an intersection, when it needs to turn, it would slow down. And then once you make the turn, you would accelerate. And once you see other pedestrian, these blue agents are like pedestrian. You will slow down and then trying to allow the pedestrian across the street and move. So all these are all automatically computed based on the probability field and the motions of these different pedestrians or obstacles. So hopefully that kind of gives you some idea how the overall approach works. So the agent have different shapes. The cars will have a different shape compared to, for example, the buses and also the pedestrian. The pedestrian, we are assuming they look like a cylinder, as you see here. And so all these are taken into account as we WAP these probability field. We call this software system WAP drivers. This is extensible to 2D agent, mostly on 2D surfaces, but it can be generalized to 3D. This is very easy to compute because we are computing a probability field offline, and then we are WAPing it around in real time. It can also be applied to 3D, like drones, capturing formation of birds and fish and so on in the 3D world as well. So next, I'm going to talk a bit about how we can extend some of these work to learn driving. So the collision avoidance algorithm that you saw there was the basis of our learn driving, the autonomous driving, along with the traffic animations. The traffic animation we use help us learn what a traffic will look like. And so when we create an autonomous driving simulator, we can incorporate the traffic into our autonomous driving simulator. And so the idea of a learn driving here, that it's different than most of the prior work that we have, is based on the idea that the training data that we use for autonomous driving are usually collected by from the human drivers. And most of these data that we collected are largely safe driving, meaning that human drivers typically would drive very safely. It rarely run into accident. And so it's kind of like a baby learning how to walk. I'm sorry, yes? Was there a question? Okay,
No,
so
ma'am.
it's kind of like baby learning how to walk. If the baby never ran into obstacle, the baby will never know how to handle obstacles. So if you have human driver always drive safely, never run into an accident, then the autonomous vehicle would not know how to deal with unsafe driving. And also, these data are also collected through human driver, but there's usually another human who would label these data. This is very, very inefficient and error prone. So nearly end-to-end systems of autonomous driving are limited to also lane following, basically following the road. And human will need to take over and control when the lane changes is demanding. And so this is some of the challenges and the problem that we are trying to solve in our approach. So our goal here is to develop an end-to-end control policy that can model the temporal sequences and process the input from a single front-facing camera to perform both normal driving and collision avoidance. So we want to teach an autonomous vehicle how to drive and how to avoid obstacle. And the approach that we adopt and that we propose here is to develop a simulation platform that will parameterize the environment setting, grounded on the transportation engineers and accident analysis study. So basically, we are looking at an environment setting, including fog, visibilities, a little squirrel crossing the street, a little child crossing the street from the middle of nowhere. And we are looking at all these different cases of what can possibly lead to accident. So then we simulate these different cases to create accidents in the simulation. Once we create an accident in our simulation, we have an automatic analysis system that will look at every single accidental scenarios using the probabilistic multi-agent simulation to generate and annotate the data that we get from the simulation, the simulated accident data. And so this will give us a way to automatically annotate these data, one of the problems that I mentioned earlier. And then we use a machine learning technique that's using a combination of LSTM and CNN architecture to continuously teach the autonomous vehicle how to learn from these annotated accident data and learn how to avoid collision from these simulated accidents. So that's the basic idea. Okay, so an overall system diagram hopefully will give you the idea here. We have a simulation platform that will simulate all kind of environment factors. And we have a real world network that will have the traffic data embedded to allow us to get the simulated data. And then we have an accident analysis module that will take the simulation with accident and then figuring out what are some of the critical events and also get these simulated camera images for the autonomous vehicle to analyze and learn how to drive. So these are just the basic idea. And through the learning module, our system will automatically classify these different road conditions, will classify the accidents, will learn how to have a control policy to teach the car how to turn the steering wheel. And the accident annotation, it can be seen here. So just to kind of give you some idea, these are different possible way of driving on the highway as you do the road changing. Every single one of this can potentially have a really critical events. With the simulation data that we collected, we can automatically annotate when you can hit an obstacle like you see here. And it can automatically do a trajectory analysis. And the control network and the machine learning network, as I already mentioned here, is we use an LSTM and CNN architecture. We could learn this from basically temporal sequence from the simulations. And we can also use this on a large number of images that we collected from the front camera simulations. So just to kind of show you the results. So as you can see here, as I already mentioned, what our contribution is basically a control policy that learn how to drive from simulated accident data. And we will show you the test results. You can see these are simulations generated by our simulator. Our approach is shown on the right, and the prior work simulator is on, ours is on the left. The prior work simulator is on the right. This is shown at 2 times the speed. So we actually purposely create the accident as you saw just in the videos, where the car actually drive into a pole. And once we were able to simulate the accident, our simulator, our machine learning algorithm will learn how to steer from the pole versus the prior simulator will run into the pole, as you could see here. So this is, about 50% slower. And you can see the car actually try to avoid the pole using our simulator, our machine learning algorithm, versus the prior work did not. They also have a machine learning algorithm, but it did not learn from the accident versus that we have. And you can also see the trajectory analysis of our simulation. So this is just the generalizations of from different cameras and from different angles that show different scenario using our approach. And again, this is a trajectory comparison for different scenario, as you can see from the prior camera. And this is one more example. It's on the curvy road. So again, on the left, that's ours. And you can see before you learn how to avoid collision, both simulator run into accident. So once it has learned the accident from the previous simulation, it actually was able to actually avoid that particular pole. And then we're able to continue drive on the curvy road as well without driving off the road, as you can see here. So it continued to drive on the road without driving off the road, versus the other simulator actually continues to drive, but it drives slightly off the road. So you can see that the trajectory that using our approach, we're able to handle the obstacle better, it stay on the road and continue to drive on the road, versus the other approach actually drive off the road. And this is, again, 4 different scenarios, different obstacles. Using our approach, it has been able to avoid the obstacle with no trouble. And again, using simulated accident analysis. And then we also show our approach also work with different weather condition. So here we actually have a thunderstorm and with the rain pulling down. And then we also have snowfalls. Our simulator is able to learn all these different kind of visibility, different weather condition, and be able to learn from these difficult scenario about how to drive safely. And so this is one of the approach, by using simulations, by using machine learning, you can actually learn from very, very unsafe road condition using simulations without actually putting a human driver in danger of actual driving to collect this kind of data. Okay, so hopefully that kind of give you some idea. So what I have presented here are learning-based approach to city scale traffic reconstruction using statistical learning and meta-based optimization, as well as probabilistic model for unified collision avoidance for vehicle, for pedestrian in a mixed complex environment. And then we apply both of these techniques to autonomous driving to help controlling autonomous vehicle and how to steer automatically to avoid collisions by learning from simulated accident. So there are definitely some limitations. Our reconstruction accuracy is currently limited by the available sensors. And also everything that you saw so far for autonomous driving are in simulation only. We still need to integrate it with an actual vehicle, but the simulation actually good as a pretty good idea how well the simulator will drive. For the future work, what we like to do is to have a higher fidelity vehicle behavior with incorporation of the driver personalities modeling as well. And we also like to use multiple fusion of data like GPS in-road data, video analysis, and survey data. And would also like to incorporate macroscopic traffic simulation in addition to microscopic in individual cars. And then perhaps adding more pedestrian behaviors, more vehicle and traffic simulation into our system. Okay, I'm gonna end right here and take questions.
Thank you, ma'am, for a fruitful session. We have a few questions from the participants, ma'am.
Okay.
Okay, the first question is, how do you identify a vehicle under moving with high speed in one particular location using GPS method?
The GPS methods will be able to collect, it may not know in a particular location, but the GPS data will tell you roughly how fast you're driving through at a certain location at a time interval. The map matching algorithm that I showed earlier, so this plot right here is going through this iterative process. It will only tell you where the GPS location is, and it need to bring you back to the network, the road network. But this iterative process where we are trying to identify the path, but then we also looking at a travel time. So a combination of travel time and the path will tell us roughly how fast the car is driving. So this location will give you the segment of the road you travel, and the travel time estimation will refine which how fast the car is driving. Now, there are certain assumptions here, and that is we are assuming that these cars are driving within the speed limit. This may or may not be the case. So certainly there are some challenges there. But it's an excellent question, and more can be done there. But what we have done is the closest approximation to what is actually going on. It will definitely satisfy the timing constraints and the location constraints. So whatever solution that we have will satisfy both. So it may not be the actual driving, but close enough. So there will be errors involved, but close enough. Okay?
Okay, thank you, ma'am. The next
Okay.
question. What is the most desirable position for mounting GPS and IMU on the vehicle body for vehicle orientation estimation?
There is really no most desirable. I mean, it's wherever you put your GPS, and most of people mount it in the front of the car simply because that's sort of where the window is, and so there will be less occlusion of the signals. But other than that, there really is, there is just a certain level of uncertainty. If you mount it in the front of the car, you will get a direct exposure. But other than that, and it's, in the center of the car would ensure that your sensor location is centering the car. So that will be really a reasonable location. But other than that, the GPS usually have about 1 meter of errors. So you can't really do any better than that.
Okay, thank you, ma'am. The last question is there pedestrian safety in intersections of road when using advanced autonomous vehicles?
Yes. So the pedestrian safety is definitely what we cares most about. As you can see in the in this simulation right here, this picture right here, we actually, for the visualization purposes, we used a blue cylinder to indicate the pedestrian safety. And so the pedestrian itself is actually smaller than the blue cylinders. And this is how we are doing the computations. Now, most of the autonomous vehicle actually have multiple sensors, if you can see it. And some of the cases that you may have heard is when the sensor miss the moving obstacles, like the squirrel or a pedestrian, it just rushed out, it was not able to see quick enough. But otherwise, most of the autonomous drivings are actually fairly safe, as long as it has adequate sensor equipped on the car. I don't know if that answered your question, because I wasn't sure I completely understand the question.
Okay, ma'am. We have 2 more questions, ma'am. Are you okay with answering them?
Yeah, sure. Go ahead.
Okay. What kind of machine learning technique or algorithm are we using to avoid accidents while driving autonomously?
Okay. So the machine learning algorithm that we have, as I already mentioned, we're using a combination of LSTM, which is also a type of recurrence network, and it's temporal-based network. And combined with CNN that will process the images. And the collision avoidance that I talk about, it was actually developed in-house. it's using a probabilistic learning-based approach by whopping the probabilistic field. We call it the WAP drivers because it's whopping the field of safety. And that probabilistic field is based on how close, imagine that it's like a digital map. It would tell you how close you are to the obstacles. So you will map the environment into an obstacle map using probability. When you definitely run into obstacle, it will be 1. And so when it's furthest away, you will be closing to 0. So we compute that for each one of the environment that the car drives, and you will be whopping around based on how the car is driving. So those are the approach that we use for collision avoidance, a combination of both. Okay.
Okay, thank you, ma'am. The last question for the session. Will the autonomous vehicles replace the pleasure of driving?
Great question. Depending on, do you like driving car or you like to just sit back and relax and to be driven? I think human driver, there are people who will always enjoy driving. And I think there will always be car that you can drive. Autonomous vehicle will be adopted probably initially, mostly for highway. The in-city driving is still very challenging for autonomous vehicle because pedestrians and human are unpredictable. And we can potentially, just sort of dash out. So I think for the foreseeable future, you will have the pleasure of driving. But even when you get old and you still enjoy driving, there will still be very, very old-fashioned car that you can use to drive. But I do think that certain, some of the share ride driving, like Ubers, like Lyft that we have in the US, and the equivalent of whatever it is in India, like Didi in China, a lot of these car share ride services may start adopting these autonomous driving to take the passengers around. So there will be a combination of hybrid of autonomous driving and still have old car that are driven by human. But I don't think autonomous driving is going to take over the world, at least not in the next 5-10 years. So maybe some of you will see my prediction in the next 5-10 years, and you can say if I call it right or wrong. But no, I don't think that your pleasure of driving will be taken away anytime soon.
Thank you, ma'am, for being so interactive. The question and answer session ends here.
Okay.
I invite Dr. G. Rohini, ma'am, Professor and Head of Lab Affairs, to express her gratitude.
Thank you, Dharni. Good evening, ma'am.
Hi.
Yeah, hi, ma'am. Good afternoon, all. Now it's time to say thanks to all. Myself, Dr. Rohini, Professor, on behalf of Department of ECE, St. Joseph's Institute of Technology, St. Joseph's Group of Institutions. Self-driving cars are the natural extension of active safety and obviously something we should do. First and foremost, I thank our guest speaker, Dr. Ming, Distinguished Professor of Computer Science, University of North Carolina, for her impressive speech on from learning-based traffic reconstruction to autonomous driving. Thank you, ma'am, for finding time and giving information on optimization techniques for traffic regulation with real-time qualitative and quantitative analysis and RAP driver, collision avoidance, robot system, despite your busy schedule for this SAVANT webinar series 2020. My heartfelt thanks to our beloved Chairman Sir, Dr. B. Baba Manoharan, for his consistent upkeep in conduction of this webinar. My sincere thanks to our Managing Director, Ma'am, Mrs. B. Jessipriya, and our Director, Sir, Mr. B. Sashi Shekhar, for their guidance in conduction of this webinar. I would like to express my gratitude to our Principal, Sir, Dr. P. Ravichandran, for his support to conduct this webinar. I also thank our Head of the Department and IEEE Student Chapter Advisor, Dr. C. Nyanakausalya, and all other faculties of our department for organizing this event successfully. A special mention of thanks to our Student Chair, IEEE WI Society, Ms. Dharani, and Student Vice Chair, Ms. Sivagaman Soundarya, third year ECE, and all other IEEE students for aiding in conduction of this webinar. Finally, I thank all the students, faculties, research scholars from India and other countries for their active participation in this webinar. Thank you all. Thank you, ma'am, once again.
Thank you, Dr. Rohini. Thanks.
Yes.
And I want to thank all the student organizer, Amira, particularly for organizing this. It has been a pleasure. And I certainly hope that some of you will be inspired to solve some of these problems. There are still a lot of challenges. And I hope some of you will work in this area in the future to help us have better traffic management for the future. All right.
Yes.
Thank you.
Yes, yes, ma'am. Sure, ma'am. We'll work on it, ma'am.
Yeah.
Thank you, Professor Ming. Thank you. Thank you for spending your valuable time with us. Thank you.
My pleasure. Okay. Best of luck. Bye, everyone.
Bye.
Bye, ma'am. Bye, ma'am.
Dharani?
Yes, sir.
Yep.
I'll just conclude the session, sir.
Okay.
I would like to thank our department heads and each one of our IEEE staff coordinators, student coordinators for taking initiative and bringing in this platform for helping the fellow students. Last but not the least, I would like to thank all the participants for their active listening and participation. Our next webinar is by an eminent speaker, Dr. Victor Villiardis, who will be giving an interesting talk on accelerating commercialization of silicon carbide power electronics, which is scheduled tomorrow at 7:30 p.m. So interested participants can register in the same link and attend the session. Thank you all.